Hi everyone, welcome back to another video on physics and maths problem solving. Today we're going to look at an IsaacPhysics problem called toppling block. It has a difficulty of 2Cs, which means it is on par with major top UK university interview standards. So definitely practicing this problem will help you a lot in your daily problem solving, as well as if you're applying to top UK universities. They do look for a lot of mastery in physics and maths in your interview. So today I'm going to go through this problem as someone who hasn't really done this problem before. Like I haven't seen this problem before making the video today. So let's get started. So the question states a rectangular block with a square base of side 10 centimeters rests on rough horizontal surface. A slowly increasing horizontal force is applied to one vertical face. If this force is applied near the bottom of the face, then as the force increases, the block will slide before it topples. If the force is applied near the top, then the block topples over before it starts to slide. When the force is applied 20 centimeters from the bottom, the block sometimes slides and sometimes topples. So the question is, find the coefficient of friction between the block and the surface to two student figures. So immediately after reading this problem, you think, okay, so this question is about static friction and the boundaries between static and dynamic friction. So let's draw a diagram illustrating this scenario here. So we have a horizontal surface, obviously, and then we have a block as such. So when you apply force to one vertical side face, if this force is applied near the bottom, then the force increases. So it's like this. There are three scenarios. Actually, made a mistake here. It should be taller because it says the side length is 10 centimeters here, and when the force is applied 20 centimeters, let's say this is 20 centimeters, when the force is applied here, sometimes the block topples and sometimes the block slides. So we know that this is the critical point. And when the force is applied at the very top, it topples without sliding, and this means there's purely torque forces involved. So let's analyze the situation here. So let's say this block has a mass of m, it has weight of mg, and so it has a normal reaction force of mu mg. Oh no, sorry, that's normal reaction force Fn, and so it has a maximum static friction of mu mg when it's been toppled, when it's sliding. Okay, so let's read the question again. So it's a rectangular block, it has a square base. Okay, so we're asked find the coefficient of friction. So let's use three information. I think using the first and the third information about when the force is applied to the bottom or top of the rectangular block doesn't serve us any use. Let's use the second piece of information when the force is applied to 20 centimeters from the surface. We know that in this case, what would happen is, okay, so definitely this force would cause like a rotation. We need to figure out where is the torque acting. So suppose that is the force coming into play, what happens is this. So okay, so there is a torque element, a rotational mechanics element to this question. Let's redraw this diagram again. So let's say this is box and this is the center of mass, and so you have mg, which is the weight, and then you have the normal reaction force. And then here you have a frictional force, mu mg, and when the force is applied, let's say 20 meters from the bottom, let's say it's applied here, there is a rotation here. And so what we know here is there is a rotation element to it, and the torques are balanced. So if we let the distance here be r, let's say this is r, this portion here would obviously be 20 minus r, right? Because the distance between here and here is 20. Okay, there is another thing that we have to clarify. Is this force above or below the center of mass? That is a question. Is it above or below center of mass? Because we would have entirely different expressions. So let me think. Is it above or below the center of mass? So let's say if this force is below the center of mass, what would happen is okay. In terms of the torques, it would be the same. Be the same torque, no matter what it is. So if it's above, so if force is above the center of mass, then the force must be greater than mu mg in order to keep the torque balanced. If the force is below the center of mass, then we have something very interesting going on. If it's below, then the distance from the force to the point there would be r minus 20. And then in this case, if it's r minus 20, I just don't think. Let's park this conversation. Come back to it later. Let's assume F is above the center of mass, just for the sake of this question. Now, if we're able to say that, then well, if it's applied there, then let's go with it. Resolving the torques. Wait a minute. There is a problem. There is a problem with the torques, and that is Okay, so if we resolve the torque around the center of mass, what we have is the force that's been pushed horizontally at the 20 centimeters above the bottom of the cube is clockwise, and so is the frictional force applied at the bottom of the cube. It's also clockwise, so the torques don't actually balance each other out. Instead, what happens is they all contribute to a clockwise torque, essentially, and so the cube would start to rotate, essentially. It starts to rotate because if F is above the center of mass, then it will definitely rotate. But if F is below the center of mass, torque cancels out. So therefore, we conclude that the force is below the center of mass. So let's just rub this out here. So we conclude that the force is actually below the center of mass at a distance r minus 20. So here, what we'd have is upon balancing the torques. So balancing torques, we have mu mg times r must be equal to F times r minus 20. This is the equation we have, and so the torques must be balanced. And what we also got to do is the forces must also balance. So what this means is F must be equal to mu mg, because for half the time the object does not spin, the object slides. So if the force is equal to mg, then mu mg, then we'll have r is equal to r minus 20, and so r is, wait, no, this is not correct. Okay, this is definitely a hard question, as seen by the 2 C's here. It's a very difficult question, so it would take about 20 minutes, I think, to solve this. Okay, slowly increasing horizontal force is applied to one vertical face. This force is applied near the bottom of the face. Then, as the force increases, the block will slide before it topples. The force applied, okay, 20 centimeters from the bottom. Do we need to know? Do we need to know the fact that this is 10 centimeters here? I'm not sure. Let's have a think. So this problem is, okay, so we've got 5 centimeters here, 5 centimeters there. Okay, so so essentially what the difference, okay, let's have a look at the hints first. Hint 1. A surface able to apply frictional force is described as rough. We know that. Move on to hint 2. So find the coefficient of friction between block and surface. Okay. Hint 3. So essentially, the hint given is saying that the force applied is actually above the center of mass and has provided us with a diagram as such. This should hopefully be sufficient. Essentially, it says this R, there's FR, there are resistive forces, there's mg, and this is 5 centimeters, and this is 20 centimeters, and this is the F. So this is the forces acting on this diagram here. Now we're asked to find mu. This is hopefully the final hint that we need. So let's think about this problem for a second. Okay, so let's resolve the forces. We know that vertically, the normal action is equal to the weight, obviously, and horizontally, I think FR must be equal to F for this to be in static equilibrium. And now we're wondering, how does the height, from the bottom to the top of the force influence whether the box get toppled or slided? For this question, okay, so we need to really think about something here. Okay, so let's take this point, the center of mass, as the point where you resolve the torques, and this point here is where you have the resistive forces. So balancing torques, you would have FR times 20 is equal to F, the force supplied, times what? Wait, no, never mind. No, never mind. I was thinking perhaps you can take account of the 5 centimeters there. Okay, so this is 5 centimeters. Okay. How is the 5 centimeters going to be useful? In this case, I don't know. I have no idea why you'd even have that 5 centimeters in the first place, but never mind. Okay, so is there a way of resolving the forces, resolving the torques, and thinking? Okay, is there a way to use the 5 centimeters and the fact that those? Okay, okay, let's have a look at the final hint. Hint 4. Final hint. So, okay. So I think what this is essentially what this is trying to say is final hint is when it's sliding, we would know that the F force supplied is equal to mu mg, which is the resistive forces, and when it's toppling, we would need to balance out the torques. And so let's think about how we can do that. Which point you want to take as the torque. Okay, so let's say mu mg is the resistive force, and let's say this is R here. I would think that mu mg times R must be equal to the force times 20 F. No, that's incorrect, because we have to try to use the fact that the distance between the side of the wall of the container and the center of mass is 5 centimeters. I have to try to use that. So let's reverse engineer the problem. If it's 5 centimeters as such, what would happen is the forces that's going to use the 5 centimeters, the torque force must be perpendicular to that. And not sure. Okay, let's have a think. So where is the point that we're taking the torques? That is a brilliant question, I think. Think about where you want to take the torques. So essentially you have so essentially you have force coming in like this, the distance. Ignore the gravitational force and the normal force for a second. Ignore that and purely consider the scenario where you have a force coming like this and a force that's sliding to the right like this. So in this scenario, we need to figure out where to take the torques. There are plenty of places where you can take the torques, obviously. Okay, so you can sort of connect it here, and okay. So where are we going to take the torque at? Is it the center of mass or somewhere else? I'll have a look at the final hint for some inspiration. Okay, so from the final hint we had was we're taking the torque from this point, essentially. That's the tip. Oh yeah, because this is the tipping point. Because imagine if you were pushing this block to the left, when it topples, it will rotate against this point. So it's not the center of mass. It's this point here. The rotation happens there. So obviously, 20F is going to equal to something. And this is going to equal to 5 times mg, because there is a normal force acting like this. So those two forces are going to balance each other, and dividing through, we get 20 is equal to 5 over mu, and hence we have mu is equal to a fourth. Let me just check the answer, see if it's correct. I think it is correct, but let's just check. It's 0.25 as the answer, which is correct.